Okay, let's get going. Yeah, hi everyone. This is Edmund Chang. I'm the host for today's seminar. So today we're very pleased to have Zhenhai Zhang to sort of come back, at least virtually, to give us a talk. Some of you might know Zhenhai, but most of the students probably didn't know him. He was a graduate from SoMAS. He graduated 2016, so probably a bit earlier than before most of you come here. But he was a PhD here. So Zhenhai got his BS from China in the Nanjing Institute for Information Science, and then came to SoMAS as a PhD student working with Professor Brian Coley. And after that, he got his PhD in 2016, as I said. And after that, he moved to California, San Diego, University of California, San Diego, the Center for Western Weather and Water Streams as a postdoc. And after a couple of years, he became a research scientist and is still working there. So some of you may remember that last year, Marty Raff actually came here to present a seminar to talk about atmospheric rivers. And I saw that Zhenhai actually published a paper with him that is related to atmospheric rivers, but also related to extratropical cyclones, and which is actually an interest for many of us here. And so we are pleased to actually welcome him back to give us a talk about, to update us about this topic. For the graduate students, Zhenhai has agreed to chat with the students after the seminar. Unfortunately, we don't have lunch today. It's hard to make virtual lunch, I guess. So after the seminar, please stay behind on the same link, and then you can chat with Zhenhai about his work, and you can chat about everything you want to chat about. So yeah, without further ado, let's welcome Zhenhai.
Thank you, Professor Chang. And I feel so glad and honored that after about 5 years, I got this opportunity to come back to SoMAS virtually and share my recent research. And as Professor Chang mentioned, during my PhD program, my research focused on the extratropical cyclones, and my advisor is Professor Brian Coley. And after my PhD, I have been working at the Center for the Western Weather and the Water Extreme, the CW3E, at the Scripps Institution of Oceanography in UC San Diego. So my current research includes 2 topics. One is about the interaction between the extratropical cyclone and the atmospheric rivers. And the second topic is the sub-seasonal to seasonal forecast. So today I will talk about my work about the influence of the antecedent atmospheric river conditions on extratropical cyclone genesis. And I want to thank my co-author, Dr. Marty Raff, for his contribution to this work. Okay, so before talking about the influence of antecedent atmospheric river AR conditions on extratropical cyclone genesis, I want to spend some time to talk about the definition of atmospheric river and the impacts of AR over the Western US. I want to talk about why the people in the Western US care so much about the ARs, especially those landfalling ARs. Okay, the first question is the definition of the atmospheric river. So as the background of this slide, it is satellite image showing the water vapor. And you can see there's a very nice atmospheric river. It's long and narrow from the subtropical ocean and extends thousands of kilometers and make landfall over the California coast. And this kind of atmospheric river, or the river in the sky, sometimes they can contain the water vapor as much as 5 to 15 times of the water flow in the Mississippi River. So that's why people call it atmospheric river. And the atmospheric river, or the AR, is defined as a long, narrow, and transient corridor of strong horizontal water vapor transport. And it is typically associated with a low-level jet stream ahead of the cold front of an extratropical cyclone. So this is a schematic showing the idealized atmospheric river. So you can see there's a low pressure center there with a cold front, and the counters here are showing the integrated water vapor. And the shades are the integrated water vapor transport, which is IVT. It is usually used to identify the AR. And you can see that ahead of the cold front, at the same position of the low-level jet, you can see strong IVT, strong water vapor transport region. And we call that atmospheric river. It is an idealized case. And these kind of ARs always make landfall along the west coast. And when those kind of ARs strike the western US, and given the topography over the western US, the warm and moist air mass easily rises up and condenses into precipitation, including the rain and all the snows over the western US. So in other words, the ARs are directly linked to the precipitation over the western US. If there's an AR, is landfalling over some region, there are always some precipitation, more or less, over that location. So that's why people are very interested in the AR concept in the Western US. And sometimes, for example, in the Southern California, for some specific locations, one strong AR case can contribute up to 50% of the annual precipitation. So those AR cases are very vital important to the precipitation over this region. Now, I want to show you a real AR case in last year to further understand the impacts of the atmospheric river on the Western US. And this figure shows the sea level pressure, the counters, and the colors and the arrows are the IVT, integrated water vapor transport. And you can see this is a well-defined AR. And actually, it is not a typical AR since it doesn't have a nearby cyclone, but it is associated with this anticyclone. And the landfalling occurs over the Washington state, and it brings heavy precipitation. Actually, this is the last AR case of a series of landfalling ARs over the Washington during the January 20 to February 10th in 2020. And those ARs brought heavy precipitation and caused serious flooding in the Washington state. And a major disaster declaration was issued for that period. So, this kind of extremely strong AR brings flooding and damage over this landfalling location. But this is just one part of this story. So during at the same time and during the next 24 hours, this same AR penetrate further into the inland region and brought snows around this pass. For example, in this region within the blue circle, the upper Colorado River Basin, there was heavy snows during those 2 days. And for example, at the one snow tile site named Tower, it got 3 feet snows in those 2 days. And the important thing is that it was not just heavy snow over the mountains. Those snowpack in the, say, this upper Colorado River Basin is very important to the water supply over the southwestern US, because the snowpack in the upper Colorado River Basin is one of the most important water source to the Colorado River, which is biggest river within the southwestern US. And meanwhile, the Colorado River is the most important surface water source for that region. So that means the snowpack plays a very important role to the water supply in that region. So from this perspective, this AR case is beneficial to the water supply over the southwestern US. So overall, the same AR case can bring disaster to the Washington state, and it also can be beneficial to the water supply over the southwestern US. So that is why people in the western US are very interested in this AR concept. And it plays a very important role in both of the water supply management and the flooding control. Okay, those are just a background of the atmospheric river and their impacts on the western US. And now we will go to talk about the main part of this presentation, the influence of antecedent AR conditions on extratropical cyclone genesis. Okay, the extratropical cyclones and atmospheric rivers, AR, they are always mentioned together since they are dynamically associated with each other. In this figure, again, the counters are the sea level pressure and the colors are the IVT. And this is a typical AR associated with an extratropical cyclone. And the extratropical cyclone has been studied for nearly 1 century, but the concept of AR was introduced in the 1990s. So the impacts of extratropical cyclone on AR are widely recognized. So the ARs are recognized as a primary region of strong water vapor transport, often created by the cyclone. However, recent studies found something new that, for example, one paper found that the ARs can span their lifetime over multiple cyclones. That means one AR is not necessarily associated with one single cyclone. They can span their lifetime over multiple cyclones. And our previous study also found that over the Eastern North Pacific, about 15% of the AR occurs without a nearby cyclone. So that means for a specific cyclone, extratropical cyclone, an AR may exist before the cyclone genesis. Now, the question is that when the impacts of cyclone on AR are widely recognized, whether a pre-existing or antecedent AR has any impacts on the cyclone genesis. Before answering this question, so first let's look at some cases. At the beginning, actually, we look at many individual cases of the cyclone genesis. So here in the case 1, you can see a cyclone genesis over the western North Pacific. And the cyclone started from a low pressure, a deep trough, And then it has first the closed circulation, which is a cyclogenesis, and then it deepens. And for this cyclogenesis case, it is dry around this cyclogenesis area. And this cyclone deepens about 400 Pascal in 12 hours. Then another case, case 2. The cyclogenesis starts from deep trough over the eastern North Pacific, and then first the circulation, cyclogenesis, and then it deepens. And for this case, it has a pre-existing AR. And this AR may be related to the low pressures at the higher latitudes. But for this new cyclogenesis, it is a pre-existing AR condition. And for this cyclogenesis, it deepens 600 Pascal in 12 hours. Then there's another cyclogenesis case. It is also occurs in the over the eastern North Pacific, and the difference from the case 2, different from case 2. The case 3 has a very strong pre-existing AR, and the cyclogenesis starts from the deep trough, and then the circulation cyclogenesis, and then it deepens. And this case deepens 1300 Pascal in the 12 hours. So just from these 3 cases, it seems like that the pre-existing AR conditions may have some impacts on these cyclogenesis. But of course, 3 cases is not enough. So we are trying to find more cases, enough cases to investigate the influence of the influence of an antecedent AR on the cyclogenesis. And specifically, we are trying to answer these questions. The first one is, what fraction of extratropical cyclogenesis events develop near an antecedent AR? And the second question is, what are the differences between the cyclogenesis with and without a nearby antecedent AR? And the third question is, how will an antecedent AR affect the cyclogenesis? So first of all, we need to find the AR and the cyclone cases. So we used the CFSR reanalysis data from NCEP, and we used the 6-hourly half-degree data, and it spans from 1979 to 2009, including 31 cool seasons. The cool season is from November to March. And we look at the whole domain of the North Pacific. And then both of the AR and the cyclones are identified objectively and independently. So first, the cyclone tracking, we used the Hodges track scheme. So it is based on 6-hourly sea level pressure. It can find the sea level pressure minimum. And we also used the minimum lifetime, the 24-hour, and minimum moving distance, 1,000 kilometers, to remove those too short or too stationary cyclone cases. So this is a cyclone tracking. And then we used the Guan and Wallace as the AR detection scheme. So this scheme uses the 6-hourly IVT, the integrated water vapor transport, which is from 1,000 to 200 Pascal. And first, this scheme will use the 85 percentile threshold to find those potential AR objects. And then there are some other requirements. For example, the length of the AR should be larger than 2,000 kilometers, and the length to weight ratio should be larger than 2, so that it will be a long and a narrow AR. And the top figure shows the basic information from the AR detection scheme. And the blue lines highlight the AR object identified for this AR case from this Guan and Wallace's AR detection scheme. So using these 2 tools, we identified all the AR and the cyclone cases within this North Pacific domain in the 31 cool seasons. Then we also used the cyclone relative composite method. So for example, this figure shows extratropical cyclone with an associated atmospheric river. And use the cyclone center, we defined a cyclone relative box. It is a very large box, 4,000 by 4,000 kilometers. And all the relevant fields within this box are saved for each cyclone center. And we repeat that every 6 hours so that we can save all of these cyclone center samples during the 31 cool seasons. And using these cyclone samples, we can create the composite fields for a specific category of the cyclone or for a specific stage of the cyclone life cycle. So this is about the cyclone relative composite. Now everything is ready. So we started to look at some results. So the first thing is that we need to categorize those cyclone genesis cases. So to do that, first we calculated the probability of AR conditions around a cyclone center. So this figure shows sea level composite sea level pressure, the contours, and the colors are probability of AR condition around the cyclone center based on all of the cyclone centers during that 31 cool season. And you can see that the high probability of AR condition is located over the south east side of the cyclone center. For example, the area of the dark red, it means that if there's a cyclone center within the North Pacific domain, then within this dark red area, the probability of AR condition is above 27%. And meanwhile, the AR conditions have large variabilities around the cyclone center. You can find those ARs around the cyclone almost everywhere except the northwest side. So this is the probability of AR conditions. And we are also interested in the AR IVT maximum positions. So for each AR, we can find the maximum IVT point. And we also calculated that related to the cyclone center. So the colors in this figure shows the number of AR IVT maximum points. And the contours shows the same thing, but for the exceptionally strong AR, which means the maximum IVT is larger than 1,250 a unit. So you can see that the IVT maximum points are more concentrated over the southeast side of the cyclone center. So based on these results, we used this blue box to define the different category of cyclone genesis. So if an AR and its IVT maximum exists within this blue box at the cyclone genesis time or 6 hours before the cyclone genesis, then those cyclone genesis are defined as cyclone genesis associated with an antecedent AR or the AR cyclone genesis. And we also selected those ARs that is exceptionally strong. So if the AR's maximum IVT is larger than 1,250, then those cases we define as AR5 cyclone genesis, following the new AR intensity scale from Marty's paper. So this AR5 cyclone genesis is a subset of the AR cyclone genesis, and we will use it to investigate the impacts of the AR's intensity on the cyclone genesis. And then the other part, of course, if there's no AR within the blue box at the cyclone genesis time or 6 hours before that, then those cases are defined as cyclone genesis without an antecedent AR. So no AR cyclone genesis. Then first, let's look at the spatial distribution of those cyclone genesis cases. So the first question is, what fraction of the cyclone genesis have an antecedent AR? So this figure, the color shows the cyclone genesis densities over the North Pacific domain. So you can see the maximum is located over the western North Pacific. So it is due to the high low-level bioluminosity over that region, and it is located at the entrance of the North Pacific storm track. And meanwhile, we also find a second cyclone genesis area over the eastern North Pacific. So overall, over the whole North Pacific domain, we found over 3,000 cyclone genesis cases in the 31 cool seasons. And overall, about 35% of those cases are AR cyclone genesis, and about 65% are no AR cyclone genesis. But this percentage varies regionally. For example, this figure, the bottom figure shows the AR cyclone genesis. And within this blue box, the Western North Pacific, only 31% of the cyclone genesis are associated with AR. But within the red box, over the Eastern North Pacific, about 55% cyclone genesis are associated with antecedent AR. Then the last figure shows no AR cyclone genesis distribution over the North Pacific. It is the opposite of the AR cyclone genesis. So this is about the distribution of cyclone genesis associated with antecedent AR. Then we are interested in the difference between the cyclone genesis with and without an AR. So here we look at the cyclone central sea level pressure deepening in 24 hours after cyclone genesis. So in this figure, the y-axis is the number of cyclone genesis per cool season, and the x-axis is the cyclone deepening in 24 hours after cyclone genesis. The blue line is no AR cases, and the red line is AR cyclone genesis cases. So overall, only about 35% of the cyclone genesis case include an antecedent AR. However, if you look at the blue and the red curves carefully, you will see that the red curve, the AR cyclone genesis, shifted to the rapid deepening side. We can see that more clearly in this figure. This is the same figure, but the y-axis is the percentage of those cyclone genesis cases in each bin, and the blue part is the no AR, and the red part is the AR cyclone genesis. In those rapid cyclone deepening part, the percentage of AR cyclone case is higher than the no AR case. So now if we just focus on the explosive cyclone genesis, the explosive cyclone genesis means the central sea level pressure decreases at least 2,400 Pascal in 24 hours after cyclone genesis. And for these cases, nearly 60% of those explosive cyclone genesis include an antecedent AR. So generally speaking, the cyclone genesis associated with an antecedent AR tended to deepen more quickly. To look at more details, we also calculated the mean time series of the cyclone central sea level pressure. And this figure shows the time series from through the cyclone genesis stage from 24 hours before to 24 hours after cyclone genesis. And the green, blue, and the red lines are for the no AR, AR, and AR5 cyclone genesis respectively. And the sea level at the beginning, the difference of sea level pressure is small, and when it's close to the cyclone genesis, the AR and AR5 cyclone genesis deepen more quickly, and it is consistent through the 24 hours after the cyclone genesis. So after 24 hours after cyclone genesis, you can see the sea level pressure difference much larger than the beginning. And the right panel shows the deepening rate of the sea level pressure for the same time period. And you can see that those AR and AR5 cyclone genesis have a higher deepening rate, especially the AR5, and it's consistent with the sea level, the change of the sea level pressure. So overall, overall, the AR cyclone genesis deepens about 50% more quickly than the no AR cyclone genesis, and the AR5 deepens even more rapidly. So these are the differences of the different category of cyclone genesis. Then we are trying to understand the reasons for these differences. So we examine the different metrics, including the water vapor transport and the diabetic processes and the dry dynamics. So first of all, let's look at the water vapor transport. So this is the composite mean IVT in 24 hours before cyclone genesis, which that period is important to the cyclone genesis. So first, the first figure shows the composite IVT for no AR cyclone genesis, and both of the colors and the arrows are the IVT. And you can see that for the no AR cyclone genesis, the IVT is very weak. And comparing to the no AR cyclone genesis, the AR cyclone genesis has nearly 80% greater water vapor inflow than the no AR cyclone genesis. And the AR5 category has nearly 140% greater water vapor inflow than the no AR cases. So it's not surprising since we defined these categories based on the AR conditions, which is mainly determined by the IVT. So now we want to understand how these differences occur. So first of all, we look at the sea level pressure, composite sea level pressure, and the sea level pressure tendency in 24 hours before cyclone genesis. So the sea level pressure pattern of the no AR and the AR cyclone genesis are quite different. For example, the high pressure for the no AR cyclone genesis is located over the southwest side of the cyclone genesis point. However, the AR cyclone genesis, it has a high pressure over the southeast side of the cyclone genesis point. The AR5 has a similar spatial pattern with the AR category, but it has a stronger pressure gradient. And because of those patterns of the sea level pressure, and you can see that there are larger differences in the low level wind. And for example, the no AR cyclone genesis, the low level wind tended to be zonal and relatively weak over the south side of the cyclone genesis point. But the AR cyclone genesis, it has a very strong low level southwest wind, which can transport the water vapor from the lower latitudes. And the AR5 cases have even stronger low level wind. And these are the low level wind. And to further understand these differences, we compared the no AR and the AR cyclone genesis at a different time point before cyclone genesis. In this figure, the colors are the difference of integrated water vapor between the no AR and the AR cyclone genesis. And the arrows are the difference of the low level wind, and the red dashed line highlighted the area of the wind convergence. And you can see that the AR cyclone genesis have more moisture available over the south side of the cyclone genesis point. And meanwhile, it also have a stronger low level wind, and it has a convergence over the south side of the cyclone genesis point. And then there's the wind is pushing the water vapor to the north, closer to the cyclone genesis point. That is at the 18 hour before cyclone genesis. Then at the 12 hour and the 6 hour before cyclone genesis, this pattern is almost the same, but the wind convergence is even stronger, and it pushes the moisture to the cyclone genesis point, the location of cyclone genesis, and the moisture difference becomes larger and larger and closer to the cyclone genesis point. And at the time point of cyclone genesis, you can see that there's the AR cyclone genesis have significantly stronger low-level wind, as well as the higher moisture over the warm side of the cyclone genesis. So that is how the AR cyclone genesis have stronger water vapor transport over the warm side of the cyclone genesis. Both of the difference of water vapor and the low level wind contribute to the difference of the water vapor transport. And then after looking at the water vapor transport, then we examine the diabetic processes. From previous slides, we know that the AR and AR5 cyclone genesis have significantly more water vapor transport to the warm sector of the cyclone genesis. So in this figure, the contours are the upward motions. It is the omega, and you can see that the AR and AR5 cyclone genesis have stronger upward motion. And given the difference of the IVT, there's a significantly stronger precipitation, and which can generate significant stronger latent heating rate around the cyclone genesis, as shown in the color of these figures. And meanwhile, the latent heating can generate the low-level potential vorticity, PV, which we call it diabetic potential vorticity. And both of the low-level PV and the low-level latent heating are favorable to the cyclone deepening, because the latent heating release will enhance the low-level circulation, which will be favorable to the deepen of the upper-level trough, as well as the upward motion. So those conditions are favorable to the cyclone genesis, to the cyclone deepening after cyclone genesis. We also examined the time series of the mean IVT and the latent heating rate around the cyclone genesis point. This is the time series of the mean IVT during the cyclone genesis period, from 24 hours before to 24 hours after cyclone genesis. So the vertical bar shows the spread of those mean IVT. The green bars are the no AR cyclone genesis, the IVT, and comparing to the no AR cyclone genesis, the blue and the red part, the AR and the AR5 cyclone genesis have significantly stronger mean water vapor transport around the cyclone genesis point. And for the mean latent heating rate, it is similar that the latent heating becomes stronger and stronger. And meanwhile, the AR and the AR5 cyclones have stronger latent heating around the cyclone genesis area. So this is about the mean sea level, mean IVT and the latent heating around the cyclone genesis. And we also calculated the low level PV, and it is very similar to the mean latent heating rate. Then we also examined the dry dynamics, which is a traditional factors contributed to the cyclone genesis. We calculated the eddy growth rate at and the 850 Pascal temperature gradient. The colors are the temperature gradient, and the contours are the eddy growth rate. And you can see that all of these three types of cyclone genesis have the strong low-level bioluminescence, and their difference is relatively small. For example, if you compare the AR and the no AR cyclone genesis, the difference of eddy growth rate around the cyclone genesis is only around 10% of a very small region of around the cyclone genesis point. And so even for the AR5 cyclogenesis, the difference of aid growth rate are not very large, around 10%. So these are the difference of the low-level balloclinicity. All of these categories, cyclogenesis categories, have strong low-level balloclinicity, but the difference between AR and no AR cyclogenesis is small. Then we also look at the upper-level forcing, including the upper-level PV, the colors here, and the upper-level jet, the counters. So first of all of these three types of cyclogenesis have favorable upper-level jet and the PV conditions. For example, the cyclogenesis point is located at the left exit of the upper-level jet, so which is a favorable region, a favorable area for the cyclone deepening. And meanwhile, comparing the no AR and the no AR cyclogenesis, the upper-level jet is in the AR cyclogenesis is about 10% stronger, and the upper-level PV, both of the upper-level PV and the upper-level jet, it has amplitude meridional structure comparing to the no AR cyclogenesis. And for the AR5 cases, it has even stronger, 80% stronger upper-level jet than the no AR cyclogenesis. But these differences are still not as large as the diabetic processes. So we also examined the time series of the mean eddy growth rate and upper-level PV around the cyclogenesis area. And these are from the 24-hour before to 24-hour after cyclogenesis. And you can see there are some small differences, but all of these differences are not statistically significant at the 95%, at the 95 confidence level. So the difference in both of the low-level balloclinicity and the upper-level PV are small and insignificant. Then I just want to show a very simple plot for the normalized percentage difference of those dry dynamics for the mean eddy growth rate and the upper-level PV. The red and blue lines are the difference of the AR and AR5 from the no AR cyclogenesis. And those percentage through the cyclogenesis stage are around or below 15%. Meanwhile, the diabetic processes, including the moisture transport at the top and the latent heating rate at the bottom, they have significantly stronger in the cyclone and in the AR and the AR5 cyclogenesis. For example, the latent heating at the cyclogenesis part, the AR cyclogenesis have about 70% stronger latent heating. Then in the last figure, I want to show the schematic summary of those differences between the no AR and the AR cyclogenesis. So these figures are based on all of the cyclogenesis cases within the North Pacific domain at the cyclogenesis time point. So comparing the no AR and AR cyclogenesis, the AR cyclogenesis have nearly 80% more water vapor inflow, the colors here. And meanwhile, it have about 10% stronger upper level jet, the blue lines here. And the eddy growth rate is similar, is not plotted here. And the PV aloft is also similar between the AR and the no AR cyclogenesis. So you can see the main difference is from the water vapor inflow and the diabetic processes. And at the cyclogenesis point, the average, the central pressure of those no AR cyclogenesis is 1,100 Pascal. But for the AR cyclogenesis, it is 1,600 Pascal. Then after 24 hours, the no AR cyclogenesis deepens about 7,700 Pascal on average. Meanwhile, the AR cyclogenesis deepened 11.600 Pascal in the 24 hour after cyclogenesis. So you compare these two numbers, you will find that the AR cyclogenesis deepens about 50% quickly than the no AR cyclogenesis. So the conclusions. First, about 35% of the cyclogenesis are associated with a nearby AR at the initial time of the cyclogenesis or before the cyclogenesis over the North Pacific. And they contribute to nearly 60% of the explosive cyclogenesis. And the second point is when the dry dynamic factors like the low-level biokineticity and up-level forcing initialize the cyclogenesis, a nearby antecedent AR can provide extra fuel, the water vapor inflow, to enhance the diabetic processes significantly, and also intensify the cyclone deepening during the cyclogenesis stage. And the cyclogenesis associated with an exceptionally strong antecedent AR deepens even more rapidly, indicating that the intensity of an antecedent AR can modulate the cyclone deepening. And these results imply that the errors in the initial conditions related to ARs can contribute to the errors in both AR and the cyclone prediction. So most of these results are summarized in these two papers. If you are interested, you can look at those two papers. And at last, I want to end this presentation with this figure. It is about the atmospheric river reconnaissance, AR Recon. And this study provided a scientific support to the AR Recon project. This project is led by CW3, our center, and the NCEP, and collaborated with the US Army Corps and the US Air Force and the NCAR. And the main goal of this project is that trying to fill the observation gap in the Pacific weather observations, mainly over the atmospheric river. Those airplanes, including the G4 from NOAA and the C-130 from the Air Force, they release the drop zone along the target region of the AR. And because below the cloud, there's an observation data gap for the ARs. So the goal of this AR Recon is trying to improve the observation over the AR and improve the weather forecast for the AR along the West Coast. Okay, that is the end of my presentation. And any question?
Okay, thank you, Zhenhai. So very nice presentation. So wow, we have a lot of raised hand. I think Jaime was the first one on the list, I guess. Jaime?
Yeah, hi Zhenhai. It's very nice to see your great presentation, and it's nice to see you keep doing a very nice, great science after still. So my question is about the figure you showed, the ETC genesis distribution over the whole Pacific, the fraction of the entire, that one. Yes, so in the Western Pacific, it's only 31.5% for the ETC with AR. Is that because the AR that meets the definition of Guan and Walliser is so the ARs in the Asia does not meet that category, so you don't have much AR that meets the category, or is it?
Yeah,
like,
that is
the reason.
Yeah, that is a possible reason. Since the AR, usually we will identify those well-defined AR as an atmospheric river, right? So, but actually there are many different AR detection algorithms. And the Guan and Wallaces, they use the many different thresholds, including the length and the length to ratio, or length to width ratio must be larger than 2. That means it must be a long and narrow, well-defined AR. So over that Western North Pacific, we know that the latent heating or the moisture plays an important role over that area to the cyclone genesis too. But those moisture transport maybe is not well defined, is not a well-defined AR shape. So we did not include those cases as AR cyclone genesis. So I know that there are some uncertainties if we use different AR detection algorithm. But overall, if we want to define the AR as a long, narrow corridor of the water vapor transport, then over that region, maybe we don't have so many AR.
Yeah, another question is about the influence of the basic state. So do you think the cyclone genesis with and without AR have some interannual like variation? The ratio is changing by some larger scale, like El Nino state, ENSO state, or MJO state, or have you done any analysis on this basic state influence?
No, I haven't looked at that, but that's a very good point. Since and you can see over the Eastern North Pacific, there are more cyclone genesis associated with an antecedent AR. And for an AR, the most important thing is the moisture, low-level moisture, and the low-level wind. So these factors may have is impacted with by the larger scale background. So if those larger scale background have impact on those low-level moisture, low-level wind, including the low-level jet over those regions, so I guess there must be some impact to the cyclone, AR cyclone, or no AR cyclone genesis.
Thank you. I have one more question, but I will ask it later.
Yeah, I think Brian, question?
Yes. Hi, Zhenhai. Great to see you again. Welcome home.
Thank you.
So a very nice presentation. So we're actually, Jaime took at least one of my questions here with regards to the Western Pacific and versus the Easterns. Maybe just to expand on that, your results seem to imply that the large scale antecedent conditions are actually very important to kind of set the stage. And so I was just curious if you have a feeling, since the Western Pacific is sort of the entrance to the storm track and the Eastern sort of the middle or the end of the storm track, are many of these Eastern cases, Eastern Pacific sort of secondary cyclogenesis events? I mean, where there was already a primary cyclone and now you're dealing with a large scale amplified trough and that sort of thing?
Yeah. First of all, I want to emphasize that even over the Western North Pacific, the diabetic processes are very important to the cyclone genesis over there. But because of because it's close to the continent, there's not many well-defined atmospheric rivers. So here the percentage is lower than the Eastern North Pacific. And as one of the case I showed here, you can see, for example, these cases are developed from the troughs, and we also saw many the second development of those cyclones. And for those cyclones over the oceans, it is very likely there's a pre-existing AR associated with a previous cyclone, or just associated with anticyclones over the ocean. And those kind of pre-existing ARs can contribute to those cyclone genesis or cyclone redevelopment over the Eastern North Pacific.
Just a quick question. I haven't looked at the more recent, but there's still a maximum in explosive cyclogenesis in the Western Pacific, right? If you do a climatology of the Pacific, most of the explosive cases are in the Western, right? In general. because of the entrance of the storm track, and yeah, there is latent heating, as you mentioned, and a strong baroclinicity. So in terms of a climatology of all cyclones, there's a maximum there.
Yes.
Okay.
Yes, I know that. There's a maximum there. The rapid explosive cyclogenesis has a maximum over the Western North Pacific, and that's true. And one thing I want to emphasize is that here we define the cyclogenesis, AR cyclogenesis, based on the time point of cyclogenesis or before the cyclogenesis. So after cyclogenesis, say 12 or 24 hours after cyclogenesis, maybe the cyclone will create associated with AR around the cyclone. So those cases still have a chance, have the contribution from the diabetic processes and have a rapid deepening rate.
Yeah, that makes sense. Thank you, Zhenhai. Nice to see you.
Thank you.
Yeah, let me just follow up on this question before I let Ming-Hua ask your question. Is that, yeah, as Brian mentioned, have you actually tried looking at separating the cases into East and West Pacific just to see whether there are differences between them? Because the large scale environment is kind of different between the jet and the storm track entrance and the jet storm track exit region. So it might be interesting to actually look at whether there is specific any difference between those two regions.
Yeah, that's a great point. Since because of the background or the larger scale conditions of these two different domains, there must be some difference. And I haven't compared the cyclogenesis within the Western and the Eastern North Pacific, but I plan to look at more details about the AR related cyclogenesis over the Eastern North Pacific. And I think it's worth to compare these two. And with a focus on the Eastern North Pacific, since those cyclogenesis or the cyclone redevelopment, those cases are very close to the West Coast of the US. And those cases, if there's an antecedent AR, those cases tend to develop very quickly, and they usually have high impact on the West Coast. So there will be a challenge for the model forecast for those kind of cases. So we will look at more details to deepen our understanding to those cyclogenesis cases. And of course, we will compare it to the Western North Pacific, and that will give a bigger picture of all those cyclogenesis in the North Pacific.
Yeah, I think that definitely makes sense, since the Eastern Pacific ones are the ones that will affect your weather, obviously, over the US. But yeah, Ming-Hua, you have a question?
Yes, I enjoyed your talk, Zhenhai. Thank you.
Thank you.
Yeah, so you showed the impact of the antecedent rivers on the deepening rate and the intensity of the cyclones. Did you look at the impact on the frequency, whether it's more likely to have cyclogenesis or not?
I haven't looked at that. I just look at the difference of deepening rate. But it's very interesting point that since it will be challenging to investigate the cyclone, the AR's impact on the cyclogenesis, since it is very difficult to define if this cyclogenesis is caused by the AR, this antecedent AR or not. But overall, we believe that the traditional dry dynamics, including the low-level baroclinicity or the upper-level forcing, the critical are the most important factors contribute to initialize the cyclogenesis. And in this study, we want to emphasize that the pre-existing AR can provide extra water vapor inflow to those cyclogenesis to enhance those cyclone deepening. But yeah, I would think about that how we can quantify the AR's contribution to the cyclogenesis frequency. Yeah, that's a good point, and I needed to think about this more.
Yeah, so I think most likely it's not. The impact may not be obvious based on your GI dynamics matrix, like the AD growth rate.
Yeah.
Mm-hmm.
Yeah.
Okay, thank you.
Thank you.
So Ping.
Yes, thank you. Zhenhai, very nice talk. Enjoyed
Thank
it.
you.
Yeah, I got a small question about the plot you're showing now on the screen. It's about 60% of the explosive genesis included AR, 35 include AR. Now, you use AR here. Can we assume that the AR here not well, all the same, or they are different, such as for those explosive genesis, the AR could be different, such as stronger, for example, or some other differences? Did you look at those differences?
Yeah, that's a good point. That's we can look at. Do you mean that we can compare those antecedent AR for those all cyclogenesis and the explosive cyclogenesis?
Yeah.
Yeah, I haven't looked at that, but I guess there must be some difference. Okay. If we can compare the AR and the exceptionally strong AR, the AR5, those two kind of ARs, they have different contribution to the cyclogenesis. The AR5 category can deepen, can enhance the cyclogenesis even more greatly. So that is from the AR perspective. But yeah, it will be interesting to, from the other side, from the different cyclone, for the different cyclones to look at the related ARs.
Yeah, maybe one small step further, that if we have AR there, would there be a genesis?
Can you repeat that?
If we have a river AR present somewhere in that region, how much chance we can see genesis?
Yeah. Yeah, that will is a little bit difficult things.
Yes.
Yeah.
Well, it's the other way around, the conditional probability, well, statistically.
Yeah, maybe we can do some statistical analysis for that question.
Yeah.
Yeah, this is similar to Professor Zhang's question.
Yeah. If
an AR can impact the cyclogenesis itself, not just the deepening.
Yeah. Okay, great.
Thank you.
Okay. Yeah, I think Jaime has a question. I think let's have this as the last question, since we've been asking him.
Thank you. So you mentioned you are also interested in S2S forecast, and in SoMAS we have like many people are interested in S2S prediction and predictability. Can you let us know what activity is going on in your institute about the S2S forecast of AR? I mean, is it like AR frequency forecast? Is it operational, like how good are the skill of the models and so on?
Yeah, actually in CW3, our S2S group has been developing subseasonal AR outlook, which means beyond the weather time scale, with a focus on the forecast time week 3. So we use 4 dynamic models to create those tools to predict the AR activity in week 3. And actually, I'm preparing a manuscript about the multimodal scale assessment about the AR related water vapor transport over the west coast of US. So specifically, we use the hindcast from the ECMWF, ECCC, NCEP, and NASA's GMAO to evaluate the model's forecast scale of the weekly mean AR water vapor transport in week 3. Since we found that there's some skill, still some skill for some specific region in week 3, but for week 4, there's nearly no skill over the whole domain. So we evaluated those hindcast systems, and we also developed near real-time subseasonal AR outlook. And because California Department of Water Resource, the folks there, they are very interested in the extended forecast. So for the week 3, so we developed those tools, and we are trying to evaluate the skill. So yeah, if you are interested, I can send you a link to our the website of our near real-time subseasonal forecast products on our website.
That will be great. Thank you so much.
Thank you.
Yeah, thank you very much for a great presentation. So